Hey guys, welcome to today's class. Have fun.
Welcome to class today. So today we'll be looking at current electricity, electric circuits, electrical energy and power, EMF, which means electromotive force, and circuits. So today we'll be looking at a very important aspect of physics, which is electricity, the electrical energies and various forms of electricity which we can encounter, and it is a very practical aspect of the subject. So firstly, we'll be looking at what electric current is. The source of every form of electricity starts with a basic electric current. Now, electric current refers to the flow of charge per unit time. Now, the flow of charge per unit time. Now, a charge, which can say it's electrons, is the basic carrier of electricity. So, the flow of charge per unit time is also referred to as electric current. So, this refers to simply the the charge that flows per unit time. So, and this charge which flows per unit time, the continuous flow of such charges, which is the current, is what we refer to as electricity. So, the continuous flow of charges per unit time through a conductor is what we refer to as electricity. So, the formula for current, electric current, is given as charge over time. Like I said, electric current refers to the flow of charge per unit time, and this is charge, electrons per unit time. That's charge over time. So our charge is equals to the current times the time. So the unit for electric current is amperes. So that is as amperes, short form amp, or can use just capital letter A. Okay, so move on. Now we'll be looking at potential difference. Now, potential difference talks about the amount of work done in moving a unit positive charge from a point to another. Like I said earlier, now we have a charge. Now, the flow of this charge per unit time is what referred to as electric current. You have a charge. Now, the amount of work done in moving this charge from a point A down to another point B is what we refer to as potential difference, PD. So the potential difference simply talks about the amount of work done in moving a unit positive charge from a point to another. So let's take, for example, a simple conductor now. Now this is an electric wire. For example, a cylindrical shape. Now you have electricity coming from a source passing through this wire, fast movement of electrons, electric currents. Now the amount of work done which is necessary to carry a charge from this point A of that conductor to B is what we refer to as the potential difference. So, and the potential difference is given as the work done over the charge, because it is the work done moving that charge from point A to point B. So, our potential difference is given as the work done over charge. So, our work done can be given as the charge times the potential difference. So, and the unit for our potential difference is the volts. So, in most cases now, the amount of work done can mostly be used for moving a charge from a point of lower potential to a point of higher potential of electric charges. Okay, so we're looking at voltage now. Now, the potential difference between 2 points in a given electric circuit. So basically, voltage can be synonymous to the potential difference. And the voltage simply talks about the PD, which is potential difference between 2 points in a given electric circuit. Similarly, But the simple difference, or a very just simple interpretation of how to measure our voltage and potential difference now. Now let's say, for example, you have a cell, and this is a battery cell. It converts chemical energy into electrical energy. Now, by connecting a voltmeter to these ends, now what is being measured across the ends of this cell is the potential difference. And the potential difference, which is the work done in moving a charge from one point to another. So the potential difference is what is being measured here. But let's take another example. You have a battery, let's say to a switch. So you have something like this now. Now by connecting a voltmeter, okay, sorry. In this case, it is the voltage which is being measured here. You have the voltage which is being measured here. In this case now, you have the potential difference which is being measured here, or you say the voltage drop. Now because you have an electric element which is connected to the source, there is a form of resistance which is offered to the flow of current. So that change or drop in the voltage between this point is the voltage drop or potential difference. So that brings us to open circuits and closed circuits. So an open circuit is a circuit said to be open if the source of electricity is not connected to any external conductor or resistance. But when it is being connected to a resistance or a conductor, we refer to this as a closed circuit. So this is an open circuit. This is a closed circuit. As we move further, I would explain better. So now we're looking at what is a resistance now. Now the amount of opposition given to the flow of electric current is what we refer to as resistance. Now I told us earlier on we have a charge Q. Now the flow of this charge Q, what brings about electricity? Now the potential difference is the work done in moving that charge from this point to a certain point. As our work done, the PD or the voltage. Now the opposition given to the flow of the currents, the opposition given to the work done required to move from a point to another point, the opposing force is what we refer to as the resistance. So resistance simply talks about the amount of opposition given to the flow of current. So resistance is a negative force which tries to pull back current. So it is simply the reverse of continuous flow of electricity. Resistance is simply the opposition to flow of current. So a simple relationship exists here, which is resistance is equal to our voltage drop divided by the current. So you have current moving from here to here. Now you have a voltage here, you have another voltage here. And this flow of charges is what brings about the electric current. So the resistance is the relationship or the ratio of our voltage to the current. And the unit for resistance is ohms, which is given as this symbol. So by just simply modifying the equation, you can have our voltage to be equal to I multiplied by R, IR. So we have various forms of measuring our resistance now. Various forms of measuring resistance. We have the voltmeter ammeter method, from a simple practical which was carried out by Ohms. It was able to show that the resistance was a constant when the change in velocity and when the ratio of the change in velocity, change in voltage, not velocity. Now the ratio of the change in voltage to the change in current gives us a constant R, which is referred to as the resistance. Now we also have the Wheatstone bridge method. And this Wheatstone bridge method simply have a simple electrical setup where you have four resistors combined. Resistor 1, 2, 3, 4. You have a galvanometer. So from the setup, the current moving in this point is equals to the current which moves in this point, and the current here is equals to the current here. So by just simply analyzing these two equations, you're able to show the relationship between the four resistances which are connected in this form in a closed circuit. So for us to find any unknown resistance now, since we know that R1 over R2 is equal to R3 over R4, but eventually we ask to find R2, you can simply change the subject and find out R2. Or if R4 is unknown or R1 is unknown. Another method of calculating resistances from the meter bridge method. Now, this X stands for the unknown resistance. This stands for the resistance of known value already. And this stands for the length of the meter bridge, the certain length which was being adjusted. Now 100 is the standard length of the meter bridge. And this is the length in which we try to fluctuate the known resistance already to find our unknown resistance X. So these simple methods are what we'll be using in calculating resistance. But basically, from this first relationship, this R equals to V over I, and gives us V is equals to IR. Okay, so now we're looking at resistance in series and resistance in parallel. I'm talking about resistance in series. Now, when two or more resistors are connected end to end, you have a series connection between these resistors. And this is the symbol for a resistor. So what simply mean here is this. I have R1 to R2 to R3. They are connected end to end. And when I have this connection of resistors end to end, it's referred to as resistance in series. Now, in series connection of resistors, they have the same electric current running through them. The same electric current, they are coming from the same source, the same connection, same electric current runs through them because they are connected end to end. But you have different voltage drops, V1, V2. So the potential difference for this first resistor is V1. Potential difference for this second is V2. For the third is V3. So when resistors are connected in series, you have the same voltage but different. Sorry, you have the same current running through them, but you have different voltages. So for us to find our effective resistance now, it's simply the sum of the resistances R1 plus R2 plus R3 and so on. Now for resistance in parallel now, you have a connection like this. In this case now, they are not connected end to end. We have a connection like this down to the source. In this case, you have a connection like this now. And when they are connected to a common terminal now, and this is not end to end like in a straight line, their wires are being connected to one single terminal here. Different resistors coming through here. This is a parallel connection of resistances. Now in this case now, the current coming from the source at this point splits into various forms, I1, I2, I3. And in this case now, for parallel connection, you have different currents. They split I1, I2, I3. And come back to this point. They join together and go back to the source as I. So for resistance connected in parallel, you have different currents flowing through them, but they have the same voltage drop V. for series connection, you have the same current, different voltage drops. For parallel connections, you have different currents, but you have the same voltage drop. So that gives us our effective resistance now to be 1 over Re equals to 1 over R1 plus 1 over R2 plus 1 over R3 and so on and so forth. So for a resistance in series, this effective resistance is simply the algebraic sum of the resistances. Whereas for a resistance in parallel, the effective resistance, which is 1 over Re, is equals to 1 over R1 plus 1 over R2. So let's say we have a series connection now, where this is 1, 2, 3. Now our effective resistance will be 1 plus 2 plus 3, which is 6 ohms. Now we are given a parallel connection 1, 2, 3 ohms respectively. Our effective resistance will be 1 over 1 plus 1 over 2 plus 1 over 3. We find the LCM. You solve, you have a value. Now don't forget that it is 1 over Re. To find our effective resistance, that will be Y over X, which gives us the value for our effective resistance. So this is simply for series connection, and this is for parallel connection. Okay, now we're looking at Ohm's law. Ohm's law. Now Ohm's law states that the electric current in a given metallic conductor is directly proportional to the potential difference applied between its ends. Now Ohm's law tells us that current is directly proportional to potential difference. It says that for any metallic conductor, the electric current is directly proportional to the potential difference applied between its ends. So for any given metallic conductor, the current flowing through, which is charge per unit time, which is current, the electric current in a given metallic conductor is directly proportional to the potential difference applied between its ends. Now, because you have potential differences at these two ends, so provided that the temperature of the conductor and other physical factors such as the length and cross-sectional area remains constant. So provided that the length of the conductor, its length and its cross-sectional area remains constant, the currents flowing through that conductor would always be directly proportional to the voltage drop across its ends. So conductors which obey this law are referred to as ohmic conductors. That is, you have the current voltage, you have something like this. Now an increase in current results in an increase in voltage. So as you increase the current, you have an increase in voltage. A decrease in current, you have a decrease in voltage. Well, conductors which do not obey Ohm's law, you have something like this. You have something like this. They are referred to as non-ohmic conductors. So they do not obey Ohm's law of resistance. So it was from this law Ohm's law of resistance, we are able to find out the constant R. R is the constant of proportionality. I is directly proportional to V. The constant of proportionality is R, which is a constant. And like I said earlier, resistance is the opposition to the flow of currents through a metallic conductor. And we have resistivity. Resistivity simply talks about the resistance per unit length, per unit cross-sectional area of the material concerned. Now, let us not forget Ohm's law. It tells us the current is directly proportional to voltage, provided the length and cross-sectional area remains constant. That's what Ohm's law talks about. Now, the resistance per unit length, per unit cross-sectional area of the material concerned is what we refer to as resistivity. Now, don't forget from Ohm's law, the constant of proportionality between the voltage and the current is R. Now it says provided the length and cross-sectional area is constant. So resistivity simply talks about the resistance of that conductor per unit length, per unit cross-sectional area of the material concerned. So what that simply means is that our resistance depends on the length and it depends on the cross-sectional area. The resistance is directly proportional to the length. Now, as the length of the conductor increases, the resistance increases also. But resistance is inversely proportional to area. Now, the larger the cross-sectional area of the conductor, the lesser the resistance. So for a conductor of CSA A1 cross-sectional area, and a conductor of another cross-sectional A2, now this has a higher resistance compared to this, with a larger cross-sectional area, but this has a lower resistance. So the resistance here is greater than the resistance here. So by combining those two functionalities now, you have R is equals to, now this symbol here, which is rho is the constant of proportionality, which is referred to as resistivity. Resistivity is the resistance per unit length, per unit cross-sectional area of the material concerned. And the inverse of resistivity is conductivity. Conductivity is K, the inverse of resistivity. And resistivity talks about resistance, opposition to motion. Now, for you to oppose an opposing motion, you have what we refer to as conductivity, which is conduction. So this is conduction, this is resistivity. So conductivity is the inverse of resistivity. So that gives us 1 over rho. Now, if R is equals to rho L over E, you can just simply have our resistivity to be equals to RA over L. It gives us the units, which is ohms meter. Now, since conductivity is the inverse of resistivity, we have 1 over resistivity, which is L over RA. We have this, so we have ohm meter all raised to -1. So now we have a shunt and a multiplier. And what do we mean by a shunt and a multiplier? Now we have various electrical instruments. First, we have a galvanometer, we have an ammeter, we have a voltmeter. Like the name implies, a voltmeter is used for measuring voltage drops, potential difference between ends. Okay, you have an ammeter. An ammeter is used for measuring current. Likewise, a galvanometer. Galvanometer is also used for measuring current. But a simple way now exists, or a simple relationship exists between the galvanometer, the ammeter, and the voltmeter. Now, a galvanometer can be made to function as an ammeter. It can also be made to function as a voltmeter. So what this means is that a galvanometer can measure current in certain conditions, and it can also measure voltage in certain conditions. So that's what we'll be looking at in shunt and multiplier. So for us to convert the galvanometer to ammeter, you have to connect a low shunt resistance parallel to the cell. Now what does this simply mean? I want to convert a galvanometer to an ammeter. The shunt is simply the conversion of a galvanometer to ammeter by connecting a low shunt resistance parallel to the cell. So in this case, you have something like this. Now, this is our galvanometer. Now you convert a low shunt resistance in parallel. And this is the parallel connections. You have a galvanometer already, which measures the current or the current flowing through. Now, for you to be able to use that galvanometer to measure a current now, you have to convert you have to connect a low shunt resistance in parallel. So by connecting a low shunt resistance in parallel to this cell, this galvanometer will no longer be a galvanometer, but it will now become an ammeter, which can now measure currents. So the relationship is given as this. The resistance of the shunt. Now this galvanometer has its own resistance. The shunt, which is the low resistance, has its resistance. And the galvanometer also has its own current flowing through the galvanometer. Now, a certain current also flows through the whole setup. Now, for us to find the resistance of these shunts, for us to know the amount of resistance which will be connected in parallel, to be able to convert this galvanometer to ammeter, we have this simple relationship. So the resistance of the shunt is equals to the current in the galvanometer multiplied by the resistance of the galvanometer itself divided by the current minus the current of the galvanometer. Now, if you recall that voltage drop is equal when you have parallel connections. In parallel connections, you have different currents but the same voltage drop. So that's because the voltage drop in the galvanometer is equal to the voltage drop in the shunt. So that gives us IGRG equals to ISRS. Now, you should not forget that the total current flowing here is the current of the galvanometer plus the current flowing to the shunt. So it's this simple relationship which brings about RS equals to IGRG over I minus IG. Now, to convert a galvanometer again to a voltmeter now, a voltmeter measures voltage, which is potential difference. Now, you simply connect a I resistance in series to the cell. Now, for the first case, you want to convert a galvanometer to ammeter. You convert a low resistance, which is known as a shunt, in parallel to the cell. But now to convert a galvanometer to a voltmeter, this is our galvanometer. You connect the I resistance in series to the cell. And this is our voltage in the galvanometer. This is the voltage of the resistor. Now, the galvanometer has its own internal resistance, RG, and this is a I resistor, R, connected in series. So when you have a simple, when you have a I resistance connected in series to the cell, you simply have the galvanometer now measuring voltage drops. And if you recall that when you have series, you have the same current flowing through it, but you have different potential drops. So our total voltage here will be the voltage in the galvanometer plus the voltage in this current. But in this first case, they have the same voltage drop. VG is equals to VS. In this case, the voltage drop is different. So the sum of the voltages is equals to V. So that gives us IRG plus IR. Now, if you recall that when you have series connection, you have the same current flowing and different voltages. That's why we have II, which are the same. But for parallel connection, you have the same voltage, but you have different currents flowing through. So this gives us the resistance, which is V over I minus RG. And recall that this is equals to IR. So R will be equals to V over I. So from this relationship, since I is common, you can simply say I RG plus R. So by changing of subjects, you have this. The resistance of the multiplier V over I minus RG. So a shunt converts galvanometer to ammeter by connecting low shunt resistance in parallel. A multiplier converts a galvanometer to voltmeter by connecting I resistance in series. The I resistance in series is a multiplier. The low shunt resistance in parallel is referred to as shunts. So we have electrical instruments, which I explained. Now we are moving further to electrical energy and electric power. Now, electrical energy is the work done when a quantity of charge moves between 2 points of potential difference. Now, if you recall energy, Energy simply talks about the ability to do work, right? So the work done when a quantity of charge moves between 2 points of potential difference is what referred to as the electrical energy. Now, I want us to remember that the potential difference PD talks about the amount of work done in moving a point charge from one point to another. That's the potential difference PD. The amount of work done in moving that charge from A to B. And that work done is what we refer to as the electrical energy, because energy talks about the ability or capability to carry out work. So the relationship which is given as Q is equal to W over V. Now recall that the potential difference is work done in moving a unit positive charge. So that gives us our work done to be equal to the charge multiplied by the voltage. So our electrical energy is given as the charge multiplied by the voltage. Okay, so I have it here. So our work done, which is the electrical energy, is equals to charge multiplied by voltage. Now if you recall that current is equals to Q over T, our current is equals to charge per unit time. So if current is equals to charge per unit time, our charge is also equals to IT. So that gives us IT multiplied by V, gives us IVT. So our work done can either be QV, it can also be work done can be QV, work done can be ITV, which is IVT. Now our work done can also be I square RT. Now we recall that V is equals to IR. Now replace I now, change of subjects, I is equals to V over R. If I is equals to V over R, that gives us V over R CV, gives us V squared over RT. So our work done can also be V squared over RT. And since V is equals to IR, from this, which is IVT, can have IRT. So our work done can also be equals to I squared RT. So we have various forms of our work done, depending on the parameters which we are given. Now we move to electric power. Now electric power, it says the time rates at which energy is being used up is electric power. And we recall from when we discussed about machinery, machines, work, energy, and power. I told us work simply has to do with the force times distance, right? In this case now, electric charge, we are talking about the charge times the voltage. So power simply refers to work done per unit time. The time rate at which energy is being used up is what we refer to as power. So we simply just have to divide our work done or the energy by T. So work done over time is what we refer to as power. So you can have power to be equals to IVT over T to give us IV. You can have power to be I square RT over T, gives us I square R. You can have it to be V square over RT. This divided by T gives us V square over R. And the unit for energy is in joules. The unit for power is in watts. Okay, now we have electrical energy consumed. Now, electrical energy consumption, which is a form of converting the amount of energy used to monetary value now. Now, for us to know the amount of electrical energy consumed, I simply use this formula. It is a simple derivation formula. Now, because power is being consumed in kilowatts, and you are given power is equals to IV. I'm using this first. Power is equals to IV. Now, power is equals to IV, but power is consumed in kilowatts per hour. Now, this is the unit which is in watts. To convert it to power per time now, power multiplied by time, I need to multiply with the power times time. And this time is in hours. And I have this in watts. But because power is consumed in kilowatt hour, I have to convert watts to kilowatts. So I have IVT over 1000. Now for us to find the costs of this energy consumed, I simply need to multiply by the money or the amount. So let's say, for example, 1 kilowatt hour costs 5 naira. So after calculating the power used, the time rates, I convert to kilowatt hour. I simply multiply by the monetary value. So that gives me our money times current times time times voltage divided by 1000. So you can simply say our electrical energy consumption is equals to MITV over 1000. Very simple way for us to recollect. Now simply we are moving to electrical installation. And live wires, neutral and earths. Now these are basic color codes. You can represent your live wire with red or brown, your neutral with black or blue, earth wire as green or yellow. So you can either have red, black, green, or you have brown, blue, and yellow. Okay, now we're looking at electromotive forces and circuits. The electromotive force is the total energy per current obtained from a cell. It is the force necessary to drive the current. Now, and this is a source of electrical energy, a cell, or say a battery. It converts chemical energy to electrical energy. Now, the force required to push this current, or the force required to keep this current circulating throughout the circuit, is what referred to as the electromotive force. So the electromotive force is the total energy per current obtained from a cell, or is the force necessary to drive the current. So the electromotive force E, which is the sum of the voltage, the force necessary to drive this current through the medium, is equal to the sum of the voltage throughout the circuit. Now, the cell itself has its own voltage, and the circuit also has its own voltage. So that gives us E to be equal to the sum of the voltages, the electromotive force. So IR talks about the voltage in the circuit, and smaller r talks about the internal resistance of the cell. So I have V is equals to IR, as you know from Ohm's law. So V equals IR. Now for the battery, now V also equals to IR, but we represent the internal resistance with smaller letter r. So I have IR plus IR, and because it's the same current that is flowing throughout the circuit, so by factorizing out I, you can have I to be into R plus small r equals to E. So we can find our current from E, which is the electromotive force, over the resistance plus the internal resistance. So lastly, we have lost voltage. Now lost voltage simply talks about the potential difference across the internal resistance. Now I said it earlier, the internal resistance of the cell is given as the current times small r, which is this. So this refers to the lost voltage of the cell, the potential difference across the internal resistance of the cell. So now we'll quickly be looking at some past questions. And this is the last class we'll be having, unfortunately, for these tutorial classes. We've been together for about 8 weeks, solving topics, so on and so forth. It's been a really fruitful time. It's just a pity we just have to stop now because schools will be resuming soon. So I want to thank every one of us who has been listening throughout the course of these classes, the physics class, and I also partially take part of the chemistry classes. So I implore us to practice more questions, read diligently, and also remember to pray. And peradventure we have any question relating to any topics which I have treated so far, I want us to channel our complaints or questions to the foundation, Vicky's Foundation. You can check out any of the social media channels online, and I will do my best to get back to us. So I implore us to read Ada, rest well, and practice more questions. You can also check back on some of the previous topics which have been treated on the YouTube channel if you have any questions so far. So this will be the last class for now which I'll be taking, and it has been nice, imparting knowledge, one or two things into students. So quickly now I'll run through some WAEC past questions and we would call it a day. Okay, so this is a NECO 2019 past question. First question I'll be solving today. Now it says determine the current supplied by the cell in the circuits represented below. This is our cell. This is the source of electricity. You have connection of resistances. You have series connection of 4 and 2 connected in parallel to a 6 ohms resistor. We have to find the current supplied in the circuit. And recall from Ohm's law that V is equals to IR. We have to find the currents in the circuits. Now we know our voltage, which is given as 12 volts. The current is unknown. And we have to find the resistance in the circuits now, which is the effective resistance of the circuits. So we have two series connection. So for the series connection now, simply have 4 plus 2 give me 6 ohms for the series connection. Now this series connection of resistors is connected parallel to another resistor of 6 ohms. So now to find my effective resistance, because it is a parallel connection now, call that 1 over R1 plus 1 over R2. So my R1 is 6, my R2 is 6. Okay, so that gives me 1 over RE equals to 6 over 1 plus 1, 2 over 6. I have 1 over RE equals 2 over 6. So RE over 1 is equals to 6 over 2. So our effective resistance is equals to 3 ohms. Okay, now I can use this relationship. V is equals to IR. So to find current, current is the voltage over effective resistance in the circuit. Our voltage is given as 12 volts. The effective resistance is 3. That gives me 4 amperes. So the current in this circuit, current supplied by the cell, is 4 amperes, which is option D. Okay, now question 34 says we have a wire of length 0.4 meters and diameter 0.6 mm. It has a resistivity of 1.8 times 10 raised to the power minus 8. Resistivity, recall, 1.8 times 10 raised to the power minus 8 ohm meter. Now I have to calculate the resistance of the wire. I want us to recall resistivity is the resistance per unit length per unit cross-sectional area of the material concerned. So R is equal to PL over A from the formulas which I gave us. Now I have to find the resistance of the wire. We have the resistivity, we have the length, you need to find the area. And recall that the area is equal to pi r square, area of the circle, through the diameter of the wire, which is circular. We have a wire with a diameter. Now given the diameter to be 0.6 mm, the length is 0.4 meters. This is the wire. The length is 0.4 meters. The diameter here is 0.6 mm. So I convert millimeters to meters. So that's 0.6 divided by 1000. This gives me 0.0006 meters. So my area is equals to pi r square. Area is also equals to pi d square over 4. So my area is equals to 22 over 7 times my diameter square over 4. So my area So I have my area already, so I can find my resistance from this. Now my resistivity, okay. My resistivity is 1.8 times 10 to the power minus 8 ohm meters. That is ohm meters. Multiplied by the length, which is in meters. So that's 0.4. All over the area. Now the area is 2.8278 times 10 to the power minus 7. And my area is in meters square, because I converted the diameter to meter. So all over meter square. So in solving this, I'm going to have 0.0255. So it gives me 2.55 10 to the power minus 2 ohms, m square. So I'm left with ohms. So the unit is in ohms. 2.55 times 10 to the power minus 2 ohms. So option B, option E, 2.55 times 10 to the power minus 2 ohms is the answer. Okay, now this is the theory question of the same examination question. It says a battery of electromotive force 12 volts and internal resistance of 0.45 ohms is connected to a 5 ohms resistor. Calculate the current passing through the circuits. Okay, so we have a battery of EMF 12 volts. Now this is a battery, the cell 12 volts and internal resistance 0.45 ohms. It's connected to a 5 ohm resistor. We have to calculate the current passing through the circuit. And we recall that our electromotive force is equal to IR plus IR. So that is E is equal to IR plus R. So by simply having a change of subject, I can have my current to be equal to E. I gave us this formula during the course of the class. So you have to find the current passing through the circuit. That is current I. So our electromotive force, EMF of the battery was 12 volts, connected to a 5 ohm resistor 5. The internal resistance is 0.45. That's small r. So it gives me 12 over 5.45. The current here is 2.20 amperes. This is the current I which will be flowing in this electrical circuit. Now I have a past question. This is WAEC 2019. It says a device consumes 100 watts of power when connected to a 120 volt source. Calculate its resistance. So it says the device consumes 100 watts of power. The power is 100 watts when it is connected to 120 volt source. Our voltage is 120 volts. It asks to calculate its resistance. I want us to recall that power is equal to current times voltage. Power is equal to current square times resistance. And power is equal to voltage square over resistance. Now we have to find its resistance. Since we are given the power and the voltage, so we have power and voltage, we have to find resistance. So using this formula, so I have power times resistance equals to V square. So my resistance will be equals to V square over power. So resistance is equals to 120 square over 100. So that resistance gives me 144 ohms. So the answer is option D, which is 144 ohms. Okay, this is a WAEC 2015 objective question. It says an electric generator rated 12 kilowatts, 2 kilovolts distributes power through a cable of resistance 20 ohms. Calculate the power loss in the cable. Now I told the electric generator is rated 12 kilowatts. What does this mean? It's rated 12 kilowatts. That's the power rating. The power is 12 kilowatts, and 12 kilowatts is 12,000 watts. Now it has 2 kilovolts. 2 kilovolts, that's the voltage. 2 kilovolts, which is 2,000 volts. It distributes power through a cable of resistance 20 ohms. Calculate the power loss in the cable. The resistance is 20 ohms. Now you have a wire which transmits electricity. The power of the cable is this and the voltage is this. It has a resistance R. Now we have to find the power loss. For us to find the power loss, it means there's a resistance R which is being given to the flow of this current. So first I have to find the current flowing before you can find the resistance. Sorry, we are given the resistance. Before you can use the resistance to calculate the power loss. Now if you recall that power is equals to current times voltage. So to find the current flowing through this cable, that's the power divided by the voltage, which is 12 kilowatts over 2000 volts, 2 kilovolts, gives me 6 amperes. So the current flowing through is 6 amperes. 6 amperes of current flowing through. So for me to find the power loss, and recall that power is also equals to I square R. Power is I square R. Power can be IV, or power can be V square over R. Now I use this first case to find my current. Now to find the power loss in the cable. Now resistance brings about loss in the flow of current, which can cause power loss. So the power loss now equals to the current, which was found to be 6 square multiplied by 20, going to give me 720 watts. So the power loss here is option C, which is 720 watts. Now, okay, I have another object to question 38. So which of the following statements about a 3-pin plug is or are correct? The brown wire is a live wire. The fuse is connected to the live wire. The earth wire is colored blue. And I showed us during the class that I have color codings, and the live wire can either be red or brown. The neutral wire can either be black or blue, and this is brown. While the earth wire can either be yellow or green. And the fuse is always connected to the live wire, because a fuse prevents electrical damage due to high power input. Now the brown wire is the live wire. The brown wire is live wire. True. The fuse is connected to the live wire. True. The earth wire is colored blue. No. Earth cannot be only be yellow and green. So the answer here is 1 and 2. That's option C. And question 39 says the symbol illustrated above is that of a resistor which what? Now this simply means a resistor which absorbs light energy. Now this type of resistor is called a photoresistor. Now it absorbs light energy, and the absorption or radiation of light energy affects the ability or affects the amount of the resistance of this resistor. So the symbol illustrated above is that of a resistor which absorbs light energy. It is known as a photoresistor. Okay, so I have another example here. It is a wire of cross-sectional area 0.6 millimeter square, has a resistivity of 7.2 times 10⁻⁻7 ohm meters. Calculates the length of the wire that will have a resistance of 3 ohms. Okay, so given the cross-sectional area 0.6 mm square, resistivity and the resistance, we have to find the length of that wire. Now you have in millimeter square and meters. I convert millimeter to meter. Now 1 meter square is equal to 10⁻6 millimeter square. 1 meter times 1 meter is 1000 mm times 1000 mm. So in millimeter square, this is the value. So I convert this to millimeter from millimeter square to meter square. So I have 0.6 divided by 10⁻6 to give me the area in meter square. Now resistance is equals to resistivity times length over area. We have to find the length of the wire that will have a resistance of 3 ohms. So the length is RA over resistivity. Resistance times the area over the resistivity gives me 2.50 meters. So the answer here is 2.50 meters. Okay, so this is another quick example here. It says a battery of 12 volts is connected to 3 resistors PQ as illustrated. as illustrated in the diagram, determine the voltage across the resistor. Now, this is the voltage moving in, which is V is equals to 24. The voltage across this circuit. Now, it was shown that the voltage drop in R is 14 volts. Now, what would be the voltage drop in this parallel connection? Now, if you recall that for series connection, you have different voltage drops, but for parallel connection, the voltage drop here is the same. So what does that mean? The voltage drop here, V2, is different from V1. Since V2 is given as 14, so it means V1 will be equals to V minus V2, which is 24 minus 14, 10 volts. So the voltage here is 10 volts. Now for parallel connections, they have different currents, but the same voltage. So if this voltage here is 10 volts, P has a voltage of 10, Q also has a voltage of 10. So the voltage across resistor Q is 10 volts. So the answer here is option B, 10 volts. Okay, so this is a 2014 WAEC past question. It says, in the circuit diagram above, E is a battery of negligible internal resistance. Now, if the EMF is 9 volts, and the EMF of this is 9 volts, the internal resistance is negligible. Now, calculate the currents in this circuit. Let's calculate the current in this circuit. Now, you have parallel connections of 5 and 20, which is connected in series to 5 ohms resistor. Okay. So you have the EMF 9 volts. You have resistors. We need to find the currents which the cell produces. Okay. Now you need to first find the effective resistance. Now you have series here. This is in parallel. So this is designated R1 and this is R2. R2. So first I need to find the parallel summation of the resistors. So R2, which is 1 over R2, equals to 1 over 5 plus 1 over 20. Parallel connections. Find the LCM. I have 4 plus 1. So give me 5 over 20. So inverse R2 over 1 is 20 over 5. R2 is equals to 4. 20 divided by 5 is 4 ohms. So I have the effective resistance to be equals to 5 plus 4. The summation of this gives me 4 ohms. 5 plus 4 ohms give me 9 ohms. Now recall that from the electromotive force and your lost voltage, you have the current to be equal to EMF over the resistance plus the internal resistance. The EMF was given as 9 volts. Now we said the internal resistance is negligible. So I take internal resistance as 0. So I have 9 over external resistance 9. Gives me 9 over 9. I have 1.0 amperes. So it gives me B, the answer, which is 1.0 amperes. So this is a question from the reference material, which is Essential Physics. I want to be solving question 36. This is a WAEC 2000 past question. It says in the diagram above, the current passing through the 6 ohm resistor is 1.5 amperes. Calculate the current in the 3 ohm resistor and the thermal potential difference of the battery. So we are told the current passing in this resistor is 1.5 amperes. Now calculate the current passing through the 3 ohms resistor and the thermal potential difference of the battery. Now first, I want us to recall that when you have parallel connections, you have different current flowing through, but you have the same voltage drop. So when you have series connection now, for series connection, you have the same current flowing and you have different voltage. So this is just the difference between a series and a parallel connection. So what this means is that the whole of these two resistors is connected in series to this. So which means the same current is flowing through them. So first I want to find the voltage of this resistor. The voltage of this resistor V equals to IR to be equals to the current flowing there is 1.5. The resistor is a 6 ohm resistor. So that gives me 9 volts. Now, since for a series connection, you have the same current but different voltages. So it means the voltage here is different from the voltage here. So I need to find the voltage here separately. So the voltage for this other side is equals to the current times the effective resistance here. Now, because it is a series connection now, the same current flows through. So my current remains 1.5. Current remains 1.5 amperes. So for me to find the voltage in this place, 1.5 times my effective resistance. To find the effective resistance first, I'll give me 1 over 3 plus 1 over 2. So that will give me 6 into 2 plus 3. Gives me 5 over 6. So the effective resistance over 1, 6 over 5. So that gives us, okay, it gives me 1.2 ohms, which is effective resistance. So back to this. So 1.5, which is the current, multiplied by 1.2, gives me 1.8 volts. So the voltage drop here is 9 volts. The voltage drop here is 1.8 volts. So automatically, since we have a series connection, different voltage, the voltage here was 9 volt and 1.8. So if I sum these two up, 9 plus 1.8, it will give me 10.8 voltage, which should be the voltage source from this battery. But first, we have to find the current in the 3 ohms resistor. So to find the current in this 3 ohms resistor, now you recall that for series connection, you have the same current but different voltages. But for a parallel connection, you have different currents, same voltage. Now I've calculated the voltage for this part to be 9 volts. The voltage for this part was 1.8 volts. So I want to find the current now in these two resistors. And recall that V is equals to IR. And for the first resistor R1, the current I1, the voltage drop is the same for parallel connection, same voltage drop. So to find the current I1, that's V over R1, gives me 1.8 over R1 is 3. This gives me, and to find I2, V over R2, 1.8 over 2, 1.8 over 3 gives me 0.6 amperes, and this gives me 0.9 amperes. So for the 3 ohms resistor, I have 0.6 amperes. For the 2 ohms resistor, I have 0.9 amperes. So option I, question I, the current in the 3 ohms resistor, 3 ohms is 0.6 amperes. Now, if you recall that for parallel connection, you have different currents flowing through them, but they have the same voltage V, 1.8. So if I sum up this current, 0.6 plus 0.9, I have 1.5 amperes, which was the initial current flowing, 1.5. So I told us in series connection, you have the same current. 1.5 flows here, 1.5 also flows here. Okay, now so I have to find the thermal potential difference of the battery. Now, which I told us should be 10.8, 9 plus 1.8. So in another way, we can calculate it to be the total current flowing in the circuit times the total resistance in the circuit. Total current flowing in the circuit is 1.5. The total resistance of the circuit, I have this and this in series, so I have 6 plus the effective resistance here. The effective resistance RE is given as 1.2. 1.2 plus 6, so I have 1.5 times 7.2. 10.8 volts. Proves this 9 plus 1.8 is 10.8 volts. Okay, so the last question I'll be treating today, question 35. It says an electric kettle is rated 1000 watts. The rating is 1000 watts, that's the power. The power is 1000 watts. And the voltage is 250 volts. That's 250 volts. And what is the resistance of the heating element when in use? I want us to record that power is equal to IV or I square R, or power is equal to V square over R. Now calculate the resistance of the heating element when in use. R, so just do a change of subject, V square over P, the voltage 250 square divided by 1000. I have 62.5 ohms. Now it says if electricity is charged at 1.5 kobo per kilowatt hour and the kettle is used for 20 minutes each day, what does it cost per week? Now I want us to record that electric cost is MITV over 1000. MITV 1000. The monetary value, the current, the time, the voltage over 1000. Now since if electricity is charged at 1.5 kobo per kilowatt hour, power is consumed in kilowatt hour. The charge is 1.5 kobo. So this is the same as 1.5 kobo per kilowatt hour. So for every kilowatt hour you use, they charge us 1.5 kobo. Now, and the kettle is used for 20 minutes each day. What does it cost per week? Now the time it is used 20 minutes per day. We are dealing with kilowatt and hours. So that's how many hours in a day. 20 over 60. It gives us 0.333 hours per day. So and it says it is used for a week. I want to find the cost for 1 week. So for 1 week, that's 0.333 times 7 gives me 2.333 hours per week. So the time usage is 2.333 hours in 1 week. So I recall that cost is equal to MICV. So our cost now, MICV over 1000. The monetary value, which is 1.5 kobo per kilowatt hour, 1.5 kobo. 1.5 times current times time times voltage. The time is 2.333. Now our current times voltage is what? Our current times voltage is the power. Power is equal to current times voltage. And our power was given as 1000 watts. 1000 watts. All over 1000. So in solving this, we're going to have 3.5 kobo. So this is the amount we are going to pay, 3.5 kobo for this electric kettle at the rate of 1.5 kobo per kilowatt hour used for 20 minutes each day. The cost for 1 week is 3.5 kobo. Thanks for listening. Wish us success in our exam.
I hope the class was interesting. If you have questions, please drop them in the comment section or send us an email. We will love to help you further. See you in the next class.